Okay, now that we've derived our governing equation for these profile models using the Dupuy assumptions, we are ready to derive some solutions. And the first one we're going to look at is flow through a rectangular section of soil. So this is what we're talking about. We have a head on the left represented by H0, a head on the right represented by HD. The length of this rectangular section is D, and the height, well, it can be any height. We're going to assume that the height of the soil is greater than H sub 0. And so we're going to solve for two things: an equation describing the shape of that phreatic surface in the rectangular section, and it's going to end up right here at the tailwater, which is one of our Dupuy assumptions. And we're also going to derive an equation for the flow rate Q through this rectangular section. Now this solution is really useful because we can apply it to a number of different kinds of problems. Well, when do you ever have a purely rectangular section of soil? You don't, but you have situations that kind of approximate this. And of course, the biggest unknown in any of these problems is the hydraulic conductivity K. So if you're making some simplifying assumptions on the shape, it is not that big a deal. So this turns out to be a really useful equation that we can use in seepage problems, profile problems. All right, so assumptions: Darcy's law is valid, and the Dupuy assumptions, and from above we get this Dupuy-Forchheimer equation. And the way you solve a differential equation, if you've had a differential equations class, if you're this far in engineering, you should have had one. You may remember that you integrate your differential equation and then you apply boundary conditions. So after doing a double integration, we get h squared equals c1 times x plus c2. And the way we solve for c1 and c2 is we apply boundary conditions. So our first boundary condition is at x equals 0 on the left side of the problem, the head is equal to h0. So if you go back to this equation, if we plug 0 in for x, and the head is equal to h sub 0, then we've just solved for c2. c2 is equal to h0 squared. Then on the right side, when x equals d, let me go back and remind you of what this looks like. So our first boundary condition was here. Our other boundary condition is over here. So when x equals z, the head is equal to h sub d. So that's our right boundary condition. And if we plug that into our equation, we can solve for c1. It's equal to hd squared minus h0 squared over d. Now, we take both of these coefficients for c1 and c2, we plug them right back into this equation, and voila, we have this equation. If we solve this for h, take the square root of both sides, we now have a very simple equation that given hd, h0, and which are the boundary conditions on the two sides, and the length of the section d, we now have a function in terms of x that will describe how how the hydraulic head varies as you go from x is 0 on the left hand side, and so as you increase from 0 to d, this will tell you what the height of that phreatic surface is. Now we need an equation for q, and q is equal to KIA. Got a minus sign on there, I'm not sure why. For this, well, if we were using the differential function del h del x, I guess that's why. And so I is equal to del h del x, which is our Dupuy assumption version of the hydraulic gradient. And if you go back to this equation right here, which, remember, this is what we got right here after solving for those boundary conditions. If you start with this equation and you take the derivative of that equation, you get 2h del h del x equals hd squared minus h0 squared over d. So when you take the derivative of the right hand side, this goes away because it's a constant, and then we have something times x, and so the derivative of that is just whatever you had in front of x. And so we take that and we solve that, if we divide both sides by 2h. And so that is the derivative, del h del x. If you plug that back into Darcy's law, Q is equal to minus k del h del x times the area. So this is our hydraulic gradient. The area is h times 1. The height to the phreatic surface times 1. And then the h's cancel out, and we get Q is equal to k h0 squared minus hd squared over 2d. So now we have an equation for h, the phreatic surface, or the height of the phreatic surface in the rectangular section, and we have a very simple equation for the flow rate. And so these are really easy to apply. Now there are a couple of modifications of this that are kind of fun. If you say, well, what if we have some sort of infiltration or recharge on the top? That infiltration rate is basically, you can show mathematically that it's equal to del Q del X. So if you have infiltration coming in, that infiltration rate, the units are such that it represents how the flow rate changes as you go from left to right. So you're going to have one flow rate as the water comes in on the left, and as it goes, before it stayed the same. It's the same Q all the way through, but now the flow rate actually increases because of this infiltration. And that's what the infiltration rate gives you. And so if we go back to our governing equation, we say the inflow minus the outflow is equal to, or plus infiltration equals 0. So this is after the conservation of mass before we had this term. Now we're just adding this infiltration term, and we can replace that with E. And then after, again, we do a double integration, and we're going to apply our boundary conditions, find the del h del x, and insert that into Q equals minus k del h del x. H is shown above. So following a derivation process which is very similar to what we did above, you can end up with this equation, which is very similar to the one that we had before, but now we've got this term on the right hand side. Actually, let's go back and see what we had before. We had k times the head difference divided by 2d, and now we have k times the head difference divided by 2d minus e times d over 2 minus x. So this x is, again, the distance you are from the left-hand side. So Q is not constant. It increases, and this shows you how Q increases as you go from left to right. If you want to know what the total flow rate is coming out the right side, you would just substitute d for x there, and d half minus d gives you minus d half. So you get plus e times d over 2, and that would give you the flow rate on the right side. So that, and again, we skipped part of the derivation here. Part of your homework for this particular part of for this section is going to be doing that derivation. So it's kind of fun. It'll be something to look forward to. Another variation of this is confined flow. So now we have a rectangular section, but it's confined. Now the flow is literally 100% horizontal, and you end up, the equation looks, this, again, we're going back to this equation right here. So we don't have infiltration in this case. And you compare this equation with this one, and the difference is we got rid of the h squared. It's just h's, and we also multiplied times b here. And so I don't have an equation for the phreatic surface. It's not a free surface in this case. It's a potentiometric surface, meaning if you put a piezometer inside that tan zone, it would raise, the water would raise up to that blue line up above. But this is the flow rate Q. All right, again, applications for this. Analytical solutions for rectangular sections are often used to estimate flow from a line source to a line sink, for example. And this is actually a homework problem that we'll be doing a little bit later in the semester. And suppose we're going to do an excavation here. We have a river that's 85 meters away. And we're going to dig a trench here and do a French drain to lower the water table. You could represent, if you had assuming you had a low permeability barrier at some depth below this, you could represent the flow from between the river and this trench using it as a rectangular section of soil as a simple first approximation. And so the boundary condition would be the river at 5232 and the trench at 5217. And that would be, if we have one-dimensional flow from the river to the trench through this rectangular section. And you can think of, if you had a really wide levee that was trapezoidal but mostly flat in the middle and small sides, small sloped parts on both sides, you could approximate that as a rectangular section. That's another approximation. So there are a number of ways to use these equations, and they're really handy.